Okay, I'm going downstairs. When we're ready, you'll have to come over here and do the go live thing. I'm already live. We'll just have to switch to Zoom.
Got it.
Okay. All right, come on.
Hey there, everybody. Can you hear me okay?
Yes.
Yes.
Can I hear you okay? Yes, I can. Okay. Scott is getting things ready downstairs. I'm trying to figure out why my new switch isn't working. I have not gotten a response from HP. They are in big trouble. It's been a full day. Ah. Oh, John. Yep. Okay, I'm going to move you all into the room. John, can you unmute yourself so I can verify that I can hear you?
Can you hear me?
I can hear you. Okay, sounds good. I'm going to assign you all. So off with you.
Bye.
I'm going to rename us here.
Now we see you.
Hello.
Let's go.
All right. Hi there.
Hi.
Hey, Abby. How's it going? So far, so good.
I'll move Abby over to this screen so that we can look in her general direction.
Hello, General. And I'm opening up the chat there in case anything appears there.
Okay.
So who's gotten the shot? Great. That's wonderful.
2 shots.
Wonderful. I'm going to go close a curtain over here. Hang on.
I have to leave at 2:30 to rejoin the Other Worlds Arts, Science, Music Festival.
Okay. So you only have a half an hour with us.
Yeah.
Okay.
Apologies for that.
Well, we will miss you.
I gave a talk this morning about other exoplanets, and now they're having a concert of music inspired by exoplanets, and later it will be a talk on art inspired by exoplanets. So
Excellent. Are we ready to go live? Anybody have problems with that?
I don't.
Here we go. Dave's got to walk over to the other computer and hit a button, and we'll be live. All right.
Are we up?
I think our 10 seconds has elapsed.
Are we, do we exist?
We do exist, I think.
Oh, good.
Hello, everybody. Welcome
Hello, everybody.
to another exciting episode of, what is this?
Sidewalk Science.
Sidewalk Science. And, you know, we've started changing our format a little bit. 2 meetings ago, 2 broadcasts ago, we had Ivan talk to us about rationality and Bayes' theorem. And that sort of occupied us for most of our program. Last time we had Dr. Mike Albro, who talked to us about some, quote, miraculous, unquote, properties of the universe in terms of physical laws and physical phenomena. And this week we're going to have Dr. Joanne Reid, who's sitting next to me, talk a little bit about the left-handed universe and chemical with regards to specialty chemistry. Yeah. But before that, I thought we would talk a little bit about science news. One of the most exciting things that I came across this past week was information about Oumuamua.
Yeah.
Breaking news about Oumuamua. And I can certainly talk about that, but do any of our distinguished panelists want to chime in about, my guess is you've seen the news as well.
Well, the new hypothesis is that Oumuamua was we can't see it anymore, but it presumably still exists, is a chunk of mostly nitrogen ice. Now, there was a very famous astronomer who was advancing the hypothesis that it was an interstellar visitor from an advanced civilization. And the reason is because it accelerated very slightly after it left, as it was leaving the solar neighborhood. That's all. Well, that was the only part of its trajectory we saw. It was already on the way out when it was discovered. So, and there was no evidence of typical cometary gases. Comets do this, but Spitzer looked for carbon monoxide and carbon dioxide and didn't see anything.
By Spitzer, you mean the space telescope?
Space telescope, yes.
Yeah. A different one than Hubble.
Yeah.
Yes.
It wasn't true.
And that was slightly mysterious, but and the other thing that's odd about it is that whatever shape it has, it's either long and thin or flattened. Its minimum axis is much smaller than its maximum axis. So as it rotates, it gets brighter and dimmer by a large fraction. And that is a bit peculiar also.
It was saying it was sort of like this.
Yeah, well,
the
the previous hypothesis was that it was a cigar, but the data doesn't distinguish between a cigar and a plate. So, and it was assumed that it had typical, cometary albedo, how much light it reflects from the sun. And comets tend to be quite dusty. No dust was observed from this thing. And their surfaces tend to be relatively dark. So it seemed like it had to be of a fairly large size, maybe, the size of a football stadium. And the new hypothesis is that it's nitrogen ice. Nitrogen ice is very bright. It's like snow. So given how bright it seemed to be, it can be a much smaller object. And then nitrogen is difficult to detect using astronomical technology. Molecular nitrogen is difficult. And so none of the observations could basically have detected any nitrogen outgassing. And if it was nitrogen ice, and if it was outgassing, then the size and the amount of propulsion it got makes sense for a natural object. We know that there are big hunks of nitrogen ice in the solar system, particularly on the surface of Pluto. Comets are not like that. Our comets are not like that. But we really only know about comets from one solar system, and then the second interstellar object ever discovered, which was shortly after Oumuamua. I've forgotten its name now, but it was similar to a comet in the solar system. So it presumably came from a solar system similar to ours. But we don't really know what environments make everything in the galaxy. From our exoplanet work, we know that there are a lot of planetary systems that are not like the solar system. And we don't know what sort of comets those things might be associated with. So maybe there are environments that are favorable for the production of floating icebergs of nitrogen. And Oumuamua seems to have been one of those. It fits the data, and it perhaps seems more likely to most of us than the idea that it was an interstellar spaceship. I, for one, would have expected an interstellar spaceship not to just barely thrust itself away, but to make some serious maneuvers.
Yeah.
John, assuming it's a natural object, which I assume, is there any evidence that it's actually from another star system? It could be just from the Oort cloud or something in our solar system, right?
It came in with greater than escape velocity, so it must have come from beyond the Earth cloud, the Oort cloud. Sorry.
Yeah, it pretty clearly came from elsewhere, and then like John was saying, shortly after that, within the past 12 months, and probably more like 6 months ago or 8 months ago, there was a second interstellar visitor discovered. Now, it's not necessarily that we're suddenly being bombarded by these pieces of interstellar debris. It's just that we're doing a better job of looking for odd things in space now.
We're suddenly being bombarded with enormous amounts of data. These digital sky surveys are producing data at a rate that was unheard of even 5 years ago.
So when we've seen pictures of this looking like an image, isn't it true that actually it's only ever been seen as a point-like object and the shape is inferred from its changes? Is that true?
That is correct.
Right.
The shape is inferred, and the only thing we really know about the shape is that when you look at it flat on, it's bigger than when you look at it end on or edge on. We don't really know, we don't know the ratio more or less, assuming that its surface reflective properties are the same all the way around, which isn't guaranteed either. But we don't know whether it's long and thin or a pancake.
I think I saw a paper that did some sort of statistical analysis and concluded it was more like a flat object than a cylinder, but it was not a direct observation. It's more like a, hey, what kind of shapes?
Yeah, it's more likely to be one than the other, but we've never seen anything like this, so we don't really know.
One of the things that intrigues me is that I guess there's probably just one common new artist interpretation of this that's been floating around the internet on news sites and whatnot. And this common interpretation is sort of an orangish brown disc-shaped object that looks surprisingly to me like the Millennium Falcon from Star Wars.
Yes, exactly.
Yes,
I
indeed.
wonder if that artist, did that deliberately or not.
I would strongly guess yes.
But science has provided no direct or even indirect evidence that Oumuamua does in fact look like a Millennium Falcon. This is just somebody's, interpretation of a bumpy pancake kind of thing.
So I remember observing a star-like object moving slowly across the sky, getting brighter and fainter and brighter and fainter. In 1958, I think it was, and it was a rocket, a Soviet rocket that was tumbling end over end and reflecting, this was after the sunset, but the rocket was still in the sunlight. And as it tumbled, it was reflecting the sunlight in a way. It was really interesting to see that. That was.
In the early 60s, there were experiments with passive communication satellites, the ECHO project, where large metallized balloons were placed in low Earth orbit and radio signals were bounced off them. And they lasted for a few months and then they would deflate and they would turn into pancakes. And I remember seeing them tumble bright and faint and bright and faint. And in fact, I even once was doing star trails with a camera, and I hadn't noticed this when I took the photo. But when I got into the darkroom, I saw this dashed line on the negative. It had to have been one of those ECHO balloons.
Telstar.
Well, Telstar was much smaller. You
But you could watch it.
You could. The ECHO balloons were really bright.
Okay.
Yeah. All right. Well, we're about 15 minutes in, and I want to make sure that we give Joanne enough time to cover her topic, and then we'll leave time for open discussion.
Well, we've only got an hour and 15 minutes. I don't know if I can squeeze it in.
Yeah. Well, we have allocated about 15 minutes for science news, and Oumuamua seems to have monopolized that time. So we might talk about other things after your description, but let's go ahead and get started with Joanne talking to us about the left-handed universe, especially chemistry.
Yeah, I wanted to first refer back to our previous discussion, which was from Mike last week, talking about the universe and how that came into existence. And the whole idea of basic particle physics. Now, I am not a physicist, and I want everyone to know I am a chemist. I don't do physics. However, I am surrounded by physicists who actually know something. So I am going to pretend I know something and go with that. But when we begin to think about the early universe, of course, we came from this hot, dense thing, whatever it was, and we produced a whole lots of little atoms. And we don't know really a lot about it, but we produced atoms like this one. And this isn't my version of hydrogen. And there it is, it's hydrogen. It's a proton that wanders around and it collects an electron and just hangs in there. What we did, of course, is we've looked at all these trons, the electrons and the protons and the neutrons and all those other trons. And we discovered there are three basic properties which seem to be universal. Everything has mass, that is, how much does it weigh? Everything has a charge, negative, positive, neutral. And everything has a spin. And even when we begin to get into light, we don't have weights, we don't have charge, but we do have spin. And the idea of the early universe having light that was rotating, it was polarized light, and it was rotating. And at least hypothetically, it could have rotated to the right hand, or it could have rotated to the left hand. And as we began looking at these things, we discovered that the universe itself really likes to be left-handed. It spins left-handed. Okay. And of course, the first thing we ask is why. The second thing we ask is, well, wait a minute.
Can you explain what it means to spin left-handed or right-handed?
Well, again, if we have a top and you align your fingers with the spin and your thumb is up, that's a left-handed spin. And if your thumb is up and it's spinning the other direction, that's a right-handed spin.
Okay.
And so here's the question. If it's a left-handed spin, and I simply turn it upside down, isn't that a right-handed spin? And of course, the answer is no. But it's not really obvious why. And so I've come up with a couple of things here. And these things will at least help an explanation. Now, this is not a perfect explanation, but it will give you a basic idea of the idea of spin and how it works. I have a helix, a perfectly good helix. For those of you who are unfamiliar with them, this is a telephone cord. And if I take a look at this particular telephone cord, you can see that it's a helix. And the way it spins, if I line my hand up with it,
let me stretch it out.
Stretch it out. If I line my hand up with it, my right hand fits right in with it. And this is a right-handed spin, okay? Now, with the idea is, if I simply turn it over, will it be a left-handed spin? And I turn it over, and guess what? It's still a right-handed spin. Oh, so this is an analogous idea of how it works.
What happens if you try to put your left hand in this?
Now, if I try to put my left hand in here, it's not going to work. My fingers are going to cross this thing. So I have a second one. This particular one is left-handed. My left hand will follow right along with it. It's just beautymous. You can see that that's just coming in very nicely. My right hand hates it. It doesn't work with my right hand. This is analogy that we have about the spin of the universe. This is the spin of the universe. It's left-handed. It's not right-handed. And if I hold it up really closely, you can see that, yeah, one helix goes in one direction, one helix goes in the other direction. And so we have a basic idea of the spins involved in the universe, and it's left-handed.
Wow. Okay.
And you go, why? And the answer is because.
Ah, excellent answer.
Now, every mother has this answer for her children. Why? Because. Now, what effect does this have on the development and the evolution of atoms? Sooner or later, you would expect that all of this stuff would have some kind of an effect upon the atoms themselves. And as we look at the collapse of a star, and we look at the explosion of the star, which is going to spew atoms all over the universe, we take a look at them and we discover, no, atoms just sort of sit around and they're really cool about it. But the most basic of all of them, of course, is the very simple one called hydrogen. All the hydrogens get together in a star and they smash into each other and they make helium. Of course, there's a lot of helium to begin with, and they make boron, and they make beryllium, and they make carbon, and they make oxygen and nitrogen and everything else, and they just keep building up. And then they explode. And when our planets, our stars are coming along, we end up with marvelous things called carbon. Carbon. Oh, carbon is the best atom in the whole universe. And I think Mike said this just last week. Carbon is the great one. Carbon loves people. It loves everyone. It loves hydrogen. In fact, we can see a basic molecule. This is the basic molecule called methane. Notice 1 carbon and 4 thingies sitting out the edge. These are hydrogen. This is methane. Notice also the shape of it. It's perfectly symmetrical. Each of these is 109 degrees. And for all of you students of military history, this is a caltrop, right? And we think of methane and we ask, well, what is it? It's a gas. It's a regular old gas. It can be compressed, and we can have it as a liquid, but it really got to be cold and under high pressure. The other things that can happen, of course, is carbon can attach to carbon. It does it all the time. Carbons love each other, and we can have two carbons. This is ethane, cooking gas. When you turn on your stove, this is ethane, and this is what you cook with. Propane is the next one up for all of you who have barbecues. Propane is 3 carbons. Then butane for all of you who've had cigarette lighters. Butane cigarette lighters, click. Most of the time it's in the form of a liquid, but it will also be gaseous. And as we get longer and longer and longer chains, we go from gas to liquid, hexane, octane, gasoline. When you pump the gasoline, it says the octane, that's at 8 carbon. When you get up into 16 and 20 carbons, it becomes a paraffin, a wax. When you get up really high, 100, 200, 500, you get polyethylene. So when you go to your store and you pull out the jug of milk, that's your polyethylene. And it's just a big long chain of these, big long chain of carbons, just going on and on and on.
Carbons and hydrogens, right?
No, carbons and hydrogens. You got it always has 4. So you've got these carbons and they react with everybody. Let's make this react with something. This is a thingy. You notice this is a blue thingy. What happens if I remove a hydrogen and put a blue thingy on it? Well, I've changed 1 carbon. What happens if I change 2? Nothing spectacular, nothing going on here. Now I'm going to change a 3rd. And this is where the whole thing becomes really interesting. I have 2 seemingly identical copies of
A molecule, yeah.
a molecule. Both of them have a green thingy, both of them have a blue thingy, both of them have an orange thingy, and both of them have a white thingy. And yet, no matter what I do, these will not fit together. No matter how I arrange them, they're not going to fit together. In fact, they are mirror images of each other. They just don't work together. Now, we discovered, as chemists, we discovered this kind of thing long ago. Louis Pasteur was the fellow who actually discovered that when you have a carbon with 4 different things on it, you can have one of 2 physical arrangements. And these are called optical isomers. They're also called enantiomers.
Could you say that again?
Enantiomers. Ooh,
Wow.
that's chemistry.
That's big word.
So long before physicists were talking about chimeric, we were talking about optical isomers and we were talking about enantiomers. What happened was Louis Pasteur was working with tartaric acid and he crystallized it. And when he crystallized it, he saw that there were 2 separate kinds of crystals in there. And he very laboriously separated the 2 different kinds of crystals and discovered ultimately that one of them was right-handed and one of them was left-handed. We'll go into that in a moment. The whole idea of polarimetry. But since 1848, we have known about this kind of situation when it comes to carbon. And we've been aware of it for a long time. And
Sort of mirror
images.
molecules with the same chemical formula, right?
Same
Identical.
Yeah, if I were to analyze these, I would come up with carbon, blue, orange, red, and so forth, and they would be identical as far as the basic analysis was concerned. What's going on here? This is the secret that goes on with life as far as we're concerned on this planet. This is where we begin to separate into our different forms of left-hand and right-hand molecules. When we think about this, I have to begin to talk about some chemistry. The chemistry of this particular atom. We're going to think about this in terms of oxidation. That is, when I apply oxygen to this, I can apply it in such a way that I remove a hydrogen and replace it with an oxygen. This is an alcohol. It has one oxygen, and of course it has an extra hydrogen sticking out at the end. This is methyl alcohol. Do not drink this. This is poison. If I did the exact same thing over here, this is ethyl alcohol. This is drinking alcohol. This is the stuff that you can drink.
But not to excess.
Well, some of us have been known on rare occasions to be excessive. If there were 3 carbons, it would be propanol. And we can build our way up all the way there, so we can have alcohols all the way up the line, just anywhere you'd like it to be, acetyl alcohols and so forth. So this is the first stage in the process of oxidation of a molecule.
You add an oxygen to it.
We add oxygen. Oxidation, adding oxygen. The second step is that we're going to fold this together. We're going to fold in I can put this little doohickey and that little doohickey, I'd be much better off. Notice that that happens. That's what we would call a double bond. Notice that the oxygen and the carbon are now connected with 2 arms, not 1 arm, but 2 arms. This is the second stage of oxidation. This is formaldehyde. For all of you who've been involved in biochemistry and biology, when you cut up the frog, when you cut the earthworm, when you cut it up and you took it out of the jar and it stinks, that's this stuff. It's really good at preserving things. When you die, they can put this into your veins and it preserves you. So this is formaldehyde. This is the second step of oxidation. The third step of oxidation is this. This is formic acid. Where do we get formic acid? We grind up ants and distill them. Formicidi. This is formic acid. Now, this is any carboxylic acid. If I were to attach this to the ethane, it doesn't want to do it. It hates me. This is propanoic acid. So the moment we talk about a carboxylic acid, this is the form that we're talking about right there. And it just hangs onto the chain. Okay. Really cool, huh? Now, what's the fourth step of oxidation? There. No hydrogens at all. This is carbon dioxide. This is the stuff that's killing our planet. Every time you oxidize carbon, ultimately you end up here. And this is the stuff which becomes a blanket around our planet, keeping in the heat. By the way, methane is 17 times a better blanket than carbon dioxide. So this is even worse, but this will react. This will react with other stuff and we can destroy it. Once you got to here, it's going to sit there until a plant grabs onto it with its little chlorophyll and go, oh, that's yummy, and turns it into sugar and releases the oxygen back into the atmosphere. So we have here propane carboxylic acid. Now, what happens if I go one more step? If I go one more step, I'm going to add a nitrogen. I'm going to capture my little hydrogen too. What happens if I add a hydrogen right there? This is the alpha carbon. There is my nitrogen. This is an alpha amino acid. In fact, this is alanine. This is one of the essential acids, one of the essential proteins that we have in our system. It makes us work. Now, there are two different forms to this. There's this form. Notice I've got my carboxylic acid out to my left. I've got my methane over here, and I'm presenting the nitrogen to you. This is left-handed. If I do exactly the same thing, I'm going to rearrange this. I'm very good at making alphas.
As is your body, perhaps.
Yep. This is the beta version. Notice. Oops, I had it right the first time. I'm going to have to read. I'm going to bring it back to where I was. Now, again, if I present this the same way, notice that I have to turn it over. This is the right-handed version. This is the left-handed version. They are essentially the same, perfectly the same. The problem is we can't use the right-handed one. This is worthless.
Biologically.
Biologically. This is what we use. This is what we have to have. And in fact, if
What about cats? Can cats use
no, no.
bacteria?
In fact, if we look at all mammals, we look at basically all life on this planet, when it comes down to which proteins are we going to use, we only use the left-handed versions. We never use the right-handed versions. Now, in the chemistry laboratory, if I were to make these, I would make what's called a racemic mixture that would have equal amounts of both of these. If I then put this in an agar, and I put in a petri dish, and I put the little bugs in there to eat this up, the bugs would live very happily until, of course, they eat it all and then they die. What would be left over? All the right-handed stuff. All the left-handed stuff would be eaten. If I make a mixture of just right-handed stuff and I put the bacteria in, they'll die. If I just make it this way, they'll live. Wow. One of these is perfect for life. One of these is terrible for life. And which one's perfect for life? The left-handed one. Just like the left-handed universe. And we say to ourselves, oh, wow, life is left-handed, just like the universe. Oh, cool. There is this chirality to the universe, and it's reflected in our amino acids and everything else. And then, of course, we chemists go and we say, wrong. The other half of life is sugar. Without sugar, we have no energy and we die. It's really simple. It's a straightforward equation. This is glucose. And one of the most basic sugars that we have. Notice it's six-sided. You've got 5 carbons and 1 oxygen. And so if I take a look at this carbon right here, this one, you can see that this carbon has 4 different things on it. It's got a hydrogen, it's got this particular oxygen, it's got this oxygen and a carbon. So this is optically active. And this can either be positioned down or up. Oh boy. Which one is ours?
Same chemist, same
chemistry,
molecules.
Same molecule. It's just a physical position. Which one do we want to have? We want to have the one which is down. This is what we can eat. And this is right-handed. If we turn it around, this won't work. In fact, these particular things can make long chains. Chains that come out this way. and just go on in both directions. If we use this molecule, it will make cellulose, trees. If we turn it around and we do this, this makes animal fats. We make a long chain, this will make animal fats. So inside of you, all this excess adipose tissue, there it is. That's what it looks like. And it's just long chains of it. We can eat this stuff. It will also make starch. So when we eat starch, we have enzymes in our mouth that will begin to break down the starch molecules into basic glucose, which we can then eat. So the question we now have is, wait a minute, we've got left-handed amino acids and right-handed sugars. Does this mean that we are following the left-hand rule of the universe? No. It says, just like when we said, why is the universe left-handed? We ask, why is this molecule left-handed and why is this right-handed? The answer is yes.
Because.
Because. Now, I also talk about left-handed and right-handed. We should discuss a little bit about how we make this measurement, how we make this determination. We use a thing called a polarimeter. Essentially, we have a tube that we can fill with liquid, and the liquid is concentration of one of these. We have a light, and we have a detector, and we can find out how much light is coming through the tube. Then we put polarizers in between them. Now, you've all had Polaroid glasses, and you notice that it cuts out the glare. That's because your Polaroid lenses are lined up this way. You can't see light that's coming in parallel. Light, as you know, is a wave. The wave can move, and it can be this way, or this way, or this way, or this way, or this way. With the polarized lenses, we're simply saying you must be lined up with the lenses in order to see it. If it's flat, it'll stop it. If you've taken your polarized lenses and you've turned them opposite one another, you'll notice that you can actually shut the light out completely. And as you gradually turn them, everything will pass through. And that's exactly what we do with the polarimeter. We put one which is fixed and one which we can rotate. We make a solution, and we find out what happens to the light. The polarized light will come in, and it will actually be turned. In sugar, it's turned to the right. We use this measurement to determine the concentration of sugar in the solution. It's called Baume, and so you can have it up to about 63 degrees, and that's a really concentrated solution of this. If you make this, it will turn it left-handed, and this will turn right-handed, because that's the property. So we can actually measure this stuff. And so right-handedness is not just a matter of which hand it fits into, but knowing which way it's turned and then physically positioning it in your hand and going, aha, that's the way it's working. So do we have right-handed life or left-handed life? No, we have a combination of left-handed amino acids and right-handed sugars.
And DNA.
But still,
what about
DNA. We know that this isn't just a thing. We know that this forms into long chains. We take essentially a ladder of proteins and then connecting rungs, and we take that ladder and we turn it to the right. Turn it to the right so that we get a spin. We actually have this spin. This is the spin of DNA. It's right-handed. So the universe is left-handed. DNA is right-handed. Amino acids are left-handed. Sugars are right-handed. Why?
But consistently across all living things.
Consistently.
Yeah.
And we don't know why. We don't know any of the reasons for it. All we know is if you feed the right-handed sugar to a cow, it'll eat it. Now, interesting aspect. If you make cellulose instead of making starch, we can't eat it. But there are a whole variety of bacteria that do, that eat it. Oh, they just love it. They think it's great. They think it's food. And of course, if we then have these inside of our intestines, then the bugs will eat the cellulose, like a cow will eat the cellulose, and generate the alpha, which we can eat. And so a cow is basically a source of nutrition for us. It goes in and it goes in and takes cellulose, changes it into glucose, which we can eat.
The bacteria in the cow.
The bacteria in the cow, and also, of course, termites. Termites do the same thing. So the enzymes that we think about that we have work with this. We also have our friends in the bacteria, which brings up an interesting point with humans. Why don't we have these kinds of bugs inside of our system? It's at least hypothetically possible. Well, one of the reasons is we have an extremely short intestine. We are a product of our own technology. Once upon a time, we were like gorillas. We were like chimpanzees. We could eat wood and woody type products and survive quite nicely. That wasn't a big problem. Nowadays, us modern humans, if we tried to eat raw food,
Raw. Fiber.
uncooked raw food, we would starve to death. We cannot survive. We have to cook our food. Wow.
Gets a head start on breaking some of these.
Got to break it down. Now, this includes steaks and chops and all those other things. Once again, the long chain molecules, we really don't handle them well. We have to break them down, and heat will break them down. Think about an egg. When we cook an egg and the albumin hits it, it goes white. That is, it's denatured. We denature it so that we can eat it, because we can't eat the long chain molecules. We can't eat a carrot or a potato. It won't help us. But the moment we break it down and we heat it and we cook it, we break down those long starch molecules, and now you have the most wonderful food in the world. You have potatoes. And believe it, if you have a diet 100% of potatoes, you will survive. You've got to eat a lot of potatoes. You're going to eat like 5 to 8 pounds of potatoes a day. That's a bunch of spuds. But you can survive on just potatoes if you cook them. If you don't, it won't work. You're in deep trouble. So we are products of our own technology.
So one of the things I had heard is that if you change the chirality or the orientation, the handedness of a sugar, that's actually one of the artificial sweeteners that we use.
Oh yes, aspartame.
Yeah.
Is a amino acid. If you have the left-handed version, you eat it, it's fine, it becomes part of your system. If you have the right-handed version, it will stimulate your taste buds, but you don't digest it.
Right.
There are other problems that we've run into with left-handedness versus right-handedness. I'm thinking of thalidomide, when we had a racemic mixture, that is, we had both of them together, which caused all sorts of problems in the 50s, 60s. Yeah, so the whole idea of which one do we want to work with, which one is active, which one is inactive, you have to be very careful with these kinds of things. You really don't want to have the wrong ones in your system.
And it's geometry.
It's geometry.
More than,
It's
I mean, chemistry is relevant in terms of the atoms that go into making it.
Yeah.
But the geometry is very important.
Yeah. So when I do this, we can see that in one case, I've got a nitrogen that's sticking up and a nitrogen that's sticking down. That's the only difference.
Different biological properties.
Completely.
Yeah.
This is inactive in our system. This is active. This will form proteins, and this will make our DNA. And this one will excrete it. It doesn't do anything. Now, that doesn't mean it's not poisonous, because it could be. It's a possibility. It just doesn't do anything. So we're fortunate in that regard. And this is a big difference between a chemistry laboratory and a living being. Living beings will create this. In a chemistry laboratory, I'll create both of these together, and it's
Sort of indiscriminately.
well,
I mean,
it'd be
once you mix
50-50.
the chemicals together.
It's 50-50.
Right.
And so I end up with a situation in which I can't really separate these.
Which is what happened with the thymidolide.
Yeah.
Right? Is when they synthesized this medicine, they synthesized the right-handed and the left-handed version.
Mm-hmm.
And initially they thought, well, I forget which one, but initially let's say the left-handed version had
Yeah.
just assumed that the body wouldn't process it and it would be benign. Well,
And
it wasn't.
it messed things up. And so we have to be very, very careful. As we learn these things, we begin to get the idea that, boy, are we ignorant. Look at those two molecules. They look to be the same, except one has the nitrogen sticking out one side and the other one has the nitrogen sticking out the other side. This one is beneficial. This one is food. This one is not.
Right.
And so there we have the basic chemistry. And so the words chirality, we love our physicist friends. They have this particular word which they use to talk about the universe. We have optical isomers and enantiomorphs, and we have used those particular terms since about the 1850s.
I think isomer in general just refers to the geometric orientation of molecules. Right?
It just,
Or,
for instance, if I have, let me do this. Let me make a quick change here.
You're a quick change artist.
I'm a quick change artist. I'm going to think about the process of, oops, took too many pieces out. I need a piece back. Come on, back.
You have an errant hydrogen.
We have errant hydrogen all over the world. Yeah. Now, if I go back and I look at this particular arrangement.
This is like Tinker Toys for science.
Oh, this is fun. This is propane. I have an odd bond here. Bond. James Bond. No.
Propane bond.
Propane bond. So, worse than. So, there is isopropanol. Isopropane, isopropanol. This is the stuff you buy in the store. Now, what's the difference?
What do you
between,
buy it for? Isopropanol.
It's a general solvent which dissolves oils better than water does and that kind of thing.
Okay.
So if I turn it around just a little bit, this is propanol. So it's exactly the same number of molecules. It's just, where is it? This is on the end, this is terminal. If I put it in the middle, it's iso. That's isopropane, propanol. Propanol.
So one of the things that this makes me think of, Joanne, is that, there's this idea in science of complexity. And scientists don't have a good yardstick to measure complexity.
Yeah.
It's one of those things, we know it when we see it kind of thing,
Mm-hmm.
right? We know that a more complex organism compared to a simpler organism, right? A virus, for example, is a very simple, there's an argument about whether it's even alive or not getting into that, but a virus is simple, a simple biological machine, whereas a bacterium is more complex. And then an elephant is, perhaps the pinnacle of complexity.
Really? Mm-hmm. And they're big.
And big, right. But the idea of complexity is not quantifiable. There's not yet a scientific theory that allows us to measure quantitatively the complexity of something.
Which is more complex? That or that?
Right. And then also the fact that they form different isomers, different geometric shapes, that adds a layer of complexity beyond the chemical constituents.
Yes.
And
then you add biology on top of that, which says, I like that one and I don't like that one. So you get a pair of twins and you say, I like that twin, but I hate that one.
Right.
But they're twins. How do you tell the difference apart? I do.
Feed it to a cow.
Feed it to a cow.
Right. All right. All right. Well, let's open it up to if it's okay with you.
That was my basics. So remember that the world tells us it's left-handed. We have right-handed DNA. We have left-handed amino acids, right-handed sugars, and no one knows why any of this is just true.
Well, there is some speculation. We talked a few programs ago about the idea that circularly polarized light from the early sun, from the baby sun, might have imbued some of these molecules are relatively simple, right? They can form in outer space without biological agents to synthesize them.
Carbon loves carbon. Carbon loves everybody. It's everybody's friend.
So there's some speculation that the circularly polarized light of the early solar system, of the early sun, might have imposed a kind of geometry or twist on some of the progenitor molecules of life. They found some of these molecules in meteorites. They've sampled the organic chemistry of meteorites. Now, that doesn't mean that meteorites are alive. It just means that meteorites contain carbon compounds. That's what organic chemistry is all about. It's about things with carbons in them, generally speaking. So when you look at the carbon compounds that are in meteorites, which have never been a part of the Earth until they fall here, the scientists have discovered that there is a chirality, a predominant handedness to some of the complicated molecules like this that exist in meteorites. So there's some hints, at least, that nature provided a template for handedness in pre-biologic molecules.
But I wouldn't go so far as to say it's light. This formed on a substrate. This formed on a thing, a rock.
Mm-hmm.
If we look at rocks, rocks are crystalline materials. Especially things like clay, which of course we have an abundance of on the planet Earth.
Mm-hmm.
I would suggest that the template upon which these form is a far more predictive part of the process of making a molecule than it is which direction is the light spin. Because again, we can find, we take our molecules, take our carbon, take our oxygen, everything else, and just sort of splash them onto clay. They will form a whole series of identical molecules every single time, which is a structure which is formed by the clay itself. What's the nebulous thing about spinning light? I don't see it acting at this level.
Well, others
now,
have.
It might. No, they have. They have.
Okay.
They have spoken about. They have talked about. They've posited it. They said, "Well, if this is true, they don't have the experimental evidence. We have experimental evidence in chemistry. Then if I take this stuff and I line it up on a substrate, a crystalline substrate like clay, that I will be able to make the same molecule time after time after time, simply because of the way that substrate is laid down." So if I look at the substrate of a meteor, are they similar? And we say, yeah, this is a great deal of similarity in chondrite meteorites. So we look at the—
That's a carbon-rich meteorite, by the way.
Mm-hmm. Which is the most common of the forms. And so you've got the carbon that's already existing. You pick up hydrogen as you're going through places because hydrogen's everywhere. You've got some energy from stars and other starlight, which is going to allow you to do things. And you have the activation energies of the substrate itself. I think there's a far more convincing evidence. That is, I can physically do it in the laboratory. I can take light and I can spin it around. I can do a spin with a polarimeter. I can spin light around and put my molecules together, and it won't have any effect on the creation of this in my laboratory. And so I'm hesitant. Now, when we begin to get down into these kinds of things, and we're talking about quarks and gluons and all those kinds of things, yeah, because you're in an early universe with a very high density and that kind of thing. And I can say, all right, perhaps in the precursor stage to the neutron and the proton, perhaps. But once you've got these things, I'm going to be the old stick in the mud and say, no, this has gone beyond. We're now into chemistry. We're not in the physics is not going to work for you. But line it up with chemistry, line it up with a substrate. Oh, works every time.
All right, thank you. So
yeah, I'm going to be as a physicist, I'm going to be a little skeptical that
I got four of them.
yeah.
that the polarization of early sunlight could have done this, because circular polarization of starlight is a weak effect. Starlight is not strongly polarized. And the direction of the polarization is a signature of the direction the magnetic field is pointing. And in some places, the magnetic field is pointing out of the star, and in some places it's pointing in toward the star. And so if you average the circular polarization around the star, it's going to be 0. And the star is rotating, and it's got all kinds of things moving around. The polarization of the active regions on our sun switches every 22 years. So I just don't see how that could work. The circular polarization of the light coming out of a star is not related to the chirality of elementary particle interactions.
And especially when you get to all the way to atoms. This is a monster. This is far outside of the range of wavelengths.
Yeah, big molecules, certainly the poly.
And then,
well, yeah.
monsters.
Right. So the scientists that have written about this go beyond my understanding of chemistry, but there are some scientists who have put forward this hypothesis. So it may be that it's an unsolved question. Maybe that's the way that we can recognize it right now, is that life predominantly uses a consistent, every living thing from a bacteria to the most complicated thing, an elephant. They all use the same handedness of all of their biomolecules, and there's no chemistry-based reason why that must be.
Even if you look at a virus, the RNA is the right-hand helix.
Good.
So you're at the simplest quasi-life form there is on our planet, and it's right in. Why? No reason.
Well,
no reason.
In physics, we commonly see broken symmetries, and they usually reflect the fact that the underlying symmetry of the physics is unstable when you bring together matter, and so the matter collapses into one phase or another phase. It doesn't want to stay in the symmetric phase, and I don't see why that sort of symmetry breaking can't extend all the way up to living things.
That would involve
energy. What that would mean is that if you have an independent origin of life, it might well have different handedness.
On another planet.
Indeed. Right. And I would go along with that idea. The idea of life being formed from silicon is silly. If it's going to be a chain, it's going to be carbon. Now, is it possible that the amino acids in a different life form are all going to be R's, not L's? Oh, sure. Is it possible that they're going to turn this glucose upside down, inside out, backwards? Absolutely. But the carbon is still going to be carbon. The oxygen is still going to be oxygen. The nitrogen is still going to be nitrogen. That part is not going to change. Unless,
John's hypothesis sounds to me, John, I don't want to put words in your mouth by any means, but it sounds to me like your hypothesis may be that there is perhaps an underlying physical reason to select for one handedness than a broken symmetry.
My hypothesis is it's like a flipped coin.
Okay, it's completely random.
A flipped coin is a fine example of symmetry breaking, because you flip it and it's in the air and it's spinning and it's all symmetrical, and then it lands on the ground and it stops.
Yeah.
Bang, it's either heads or tails.
Okay. Thank you. Abby, haven't heard a lot from you today. Did you have thoughts about some of these chemical issues?
Biologist.
I was actually just going to add one teensy thing to what Joanne was saying, and that is where you were talking about how humans cannot survive on raw food. That experiment has been done and in fact is being done at present with the raw foods movement that exists in certain places. And I actually went to a very interesting talk about this by Richard Wrangham, who has the sort of cooking hypothesis of human evolution. And he said that among the followers of the raw food movement, even in well-developed countries like Germany, where they are allowed to process the food, you know, put it in a blender or something like that. Without cooking, basically people can survive, but they are A, very skinny, and B, the women do not menstruate.
Huh.
In other words, they're not going to reproduce.
Species dies.
The species will die if we eat nothing but raw food in our current state. And he is, I don't know if he is the first, but he is certainly the anthropologist, primatologist who has put forward the idea that that early technology of cooking was what enabled us to grow our big brains because suddenly more calories were available to us.
We didn't need as many calories dedicated to our intestines.
Yeah, and you basically, there's the way he put it is, despite what, you know, Weight Watchers will tell you, a calorie is not a calorie.
Right.
Yes.
And so you could take in basically the same food, the same number of calories if you were to measure them in a bomb calorimeter. But if those calories, if those foods have been cooked first, you will get more calories out of them. And you will get more general nutrition out of them, which means that you will have more energy to do everything with, including, you know, building a healthier body and having an immune system and good stuff like that. But also you'll have more calories left over to build a big, huge, expensive brain like ours, because brains are really energetically expensive.
Although the thing that I had noticed about the pure food movement is that they're highly selective about the foods that they're talking about. They're moving into things like lentils and peas and that kind of thing, which are relatively simpler forms. They're not talking about potatoes, they're not talking about carrots, they're not talking about turnips and squash and those kinds of things. So they're talking about pod almost to the point of fruit. You know what I mean by a pod vegetable.
Yeah, well, no, I was speaking specifically of the raw food movement.
Indeed.
One of many different food movements out there. But as I said, according to Richard Wrangham, that's some pretty good evidence that we evolved our big brains once we started cooking. So it was, in fact, pre-humans who became capable of harnessing fire. And
Yeah.
that gave us the opportunity to become human.
Yeah, if we look at potatoes as a for instance, the raw food movement, of course, doesn't do potatoes, and for good reasons.
Oh, they don't?
Well, if you have raw potatoes and you eat raw potatoes, there's an underlying skim,
That
you know,
can kill
the
you. Yeah.
green skim in there,
Yeah.
and that, of course, is a trypsin inhibitor, which will kill you.
You have to peel the potatoes.
Yeah,
You
can peel
have,
them and eat them.
so already you're peeling them, and now you're down to that big starchy component,
Right.
and it's virtually indigestible. Not completely, I'll agree with that. Whereas if you now cook that, you will get 10 times the nutritive value.
Right.
Yeah, one of
Right.
the interesting things about cooking, can I see a couple of your molecules there?
Oh, we got molecules. Boy, we got molecules.
This notion, this is probably a slightly inaccurate representation of it, but there's this concept of hydrogen bonds, that if you take a long, complicated molecule and you sort of wad it up, naturally, depending upon the geometry, some of the hydrogens will have a leftover kind of very slight electric charge, kind of like a water molecule has a leftover electric charge. That the charges in the molecules in the atoms sort of clump up, you can think, close to where the bonds are. And that leaves the places without the bond, leaves those to have a little net charge. Well, that tiny little charge can cause a lot of the complicated geometry that we see in you probably have heard of protein folding. Well, a lot of the physics and chemistry behind protein folding involves the way these minuscule charges cause these complicated molecules to fold in on themselves.
Oh, here's your example. Again, this is the amino acid. And you notice I have a hydrogen sitting out here with my oxygen. I can turn my nitrogen, all of a sudden I have a hydrogen here. And that hydrogen is suddenly being attached to. It's been thinking about.
Slightly,
notice
yeah.
there's a slight attachment there, and it would be symmetrical. And the symmetry is what would cause a certain amount of that hydrogen bonding. And so this is an open space here. It's sort of, again, a Mickey Mouse kind of a thing.
It changes the geometry.
And so all of a sudden you have a geometric change, and this is much more stable than that is.
Yeah.
This is a less stable configuration than that is.
So one of the things that happens when you cook food, so the reason I'm bringing this up is that when you cook food, you can put, relatively speaking, a low amount of energy in it. You're not putting enough energy into it necessarily to break some of these chains, although we do that sometimes with, depending upon the product of our cooking. We do that when melting some sugars and reducing them to glucose and whatnot, complicated sugars. But putting a modest amount of heat into a complexly folded molecule can break some of those hydrogen bonds and unfold the molecules. And that's part of what happens when you cook an egg, for example.
Yeah.
Right.
Now, in this case, when we're talking about our glucose problem, we're talking about starch. And again, a starch would be a series of molecules that are extending out this way, creating a long series of chains. By cooking it, that long thing, we break the bond.
Yeah, you can
We
break
physically break the bond, and we reduce the size of it. We don't bring it all the way down to glucose, but we reduce it from something that's 100 units long to something that's 5 units long. And the 5 unit long we can eat and digest.
So that's one of the things that cooking does, is it can both denature.
For
Go
us.
ahead, Abby.
So it's doing a lot of the bond breaking for us, is what I'm hearing here. And the other thing is that, when you cook the proteins and you do wind up breaking some of those hydrogen bonds so that the proteins don't have the same shape, for instance, that's the process called denaturing. And that is generally what will make something biologically inactive. And the example of the egg white is a very nice example, that an egg white inside a raw egg would in principle be able to, support a gestating chick. But man, once you cook that egg white and it turns white, there's no going back.
Yeah, you've unfolded those.
Yeah, that's one direction.
You just broke those hydrogen bonds. You wouldn't think that would be so important, but it is.
We do have a question online, or a comment. Looks like a question. Let me read this. We'll see who wants to tackle it. Peter, one of our viewers, says, how do we know there is no causal initiator for the spin orientation of the molecules you spoke of? And the second part of his question is, what modeling can be used to potentially determine this? So how do we know there's no causal initiator? How do we, who wants to tackle that one?
Well, I'll let a physicist tackle spin. I'm your chicken.
The answer is we don't. We don't know why the symmetries that we see broken in the universe. We have, in many cases, we have an idea of why they should break, but we don't have any idea of why they should have chosen heads or tails.
Yeah. Go ahead, John.
Well, go ahead. I think I've actually finished.
Okay. So one of the things we haven't touched on today that is one of my favorite topics is, strangely enough, the Higgs particle.
Ooh, our friend the Higgs particle.
And there's this notion that if something is spinning in a clockwise orientation, you could always move ahead of it. And when you move ahead of it, it looks like it's spinning anti-clockwise to your orientation when it's physically spinning, not its geometry of structure, but its spin of
But
motion.
this gives you an idea of the spin that we're
Right.
talking about.
And there's nothing that could go faster than light. That's one of the laws of nature. And it seems to be that as you approach the speed of light, the fundamental particles that build up the matter in the universe are left-handed. They have a left spin in terms of their orientation relative to their motion, if they're going fast enough. And to John's earlier point, there doesn't seem to be a good physical explanation of why they're left-handed versus right-handed. But the fact that that difference exists indicates that there is a symmetry that broke somewhere in the early universe as the universe cooled off. And these elementary particles formed out of the potential energy of the Big Bang. Well, that symmetry breaking has been associated with a field that permeates the universe, and the Higgs particle is the particle associated with that field. I don't want to get too far into this, but in modern physics, every particle has its own unique associated field, and the particle associated with the broken symmetry between left and right-handed material is Higgs. One of the other properties of the Higgs is that this interaction causes every particle to have mass. And so complicated physics is entailed in the idea of a certain handedness or orientation of spin in the universe. Ivan or John, did you want to correct or amplify anything I said about that?
Look at the silence.
Yeah.
Dead silence out there.
No, I mean, I think that's pretty good. It's just there is this idea of spontaneous symmetry breaking. It's just what John was talking about with the flipping of the coin, where in the sort of higher energy state, it's symmetric, but the ground state is not, right? That when things cool off and it goes into its ground state, it's going to be one way or another. And so this has been used in physical theories to explain asymmetries, and in the case of the Higgs, to also explain why do some particles have mass.
But that doesn't do anything.
Yeah, you
for
can't
this.
extrapolate from that to
Yeah,
chemistry.
it just doesn't carry that far.
Right.
Right.
Yeah, you can't say that left-handed electrons give rise to left-handed isomers.
No, they just
No, there's
sit there.
no connection.
They just
there.
sit there.
One of the puzzles in theoretical particle physics right now is that back when we understood this symmetry breaking, or thought we did, we thought that all neutrinos are left-handed. But now we have evidence that neutrinos have mass. And what that means is that if you were to follow a left-handed neutrino and you were to go fast enough, you'd pass it and it would look right-handed. And we don't know what right-handed neutrinos would be like.
Never detected one, right? Or
That's right.
could we detect one, John? I mean, is there some experimental apparatus that could distinguish between a left and right-handed neutrino?
Well, certainly there is experimental apparatus. Now, I don't know if any of the neutrino experiments looking at natural neutrinos are capable of doing this. I'm not sure.
Okay.
I think the answer is no, because it is a big puzzle.
Before we get too far, I wanted to go back to something that Ivan had sent out about 7,600 mosquitoes.
Oh, yes, the energy of 7,600 mosquitoes. Ivan, what was that all about?
So this is a neutrino detector. So neutrinos do not easily interact with matter. So typical neutrino might pass through, a light year of lead shielding before it interacts with the lead and is stopped by the lead. So there are vast numbers of neutrinos pouring out of the sun, which are going right through us right now. Just
Harmlessly.
Ooh, tickles.
not interacting with us. So there are neutrinos are produced in other ways. They're produced in supernovae and in radioactive decays and so on. Well, in this experiment, I don't have the article in front of me, so I don't recall the details, but they detected a neutrino that had an energy of 6,300 TeV. So it's hundreds of times more energetic than the particles at the LHC. So an incredible amount of energy in one neutrino. So one of the things you can do, physicists like to do this, right? You have a certain amount of energy in this tiny particle. You say, well, how much energy is that? And if it were a mosquito, for example, how fast would this mosquito be moving to have that much energy? Like, turns out, what was it? It was like Mach 8 or something.
Yeah. So to compensate, you have more mosquitoes with a smaller amount of energy.
Right. So it'd be like bumping into a cloud of several thousand mosquitoes.
From one particle.
From one particle, right. So it is interesting. People were concerned about what's going to happen at the LHC when they get up to these energies. Are they going to create black holes, right? What is the danger that's presented by the LHC? And the answer is, well, particles that are much more energetic than they are from the LHC hit the Earth, or maybe not all the time, but quite a lot. So we don't think it's going to create black holes. But it is interesting. I mean, one question would be, how do you produce a neutrino with that kind of energy?
Yeah, that's astounding thing.
That's a ridiculous amount of. It's what I like to say. It's a silly number.
Yeah.
Mm-hmm. So how do we get something that's
another puzzle? Is it a supernova? Is it a black hole? Is it dark matter? No. I mean, there's so many things about the universe that we don't know yet.
Could it be primordial even? I don't know.
Oh yeah, left over from the Big Bang. Now that's a cool idea.
Oh, I like that.
Yeah,
that's a good one.
Yeah. All right.
There was one other thing that came up earlier about measuring, how scientists don't have a way of measuring complexity.
Yeah.
And I'm going to say that's, I wouldn't necessarily disagree with that statement, but there are ideas about how you might do it.
Oh yeah, cool.
And one way is algorithmic complexity, which is if you're going to write a program to generate this thing, how complex would the program be?
How many lines of code? Is that what you mean?
Something like lines of code, or how many instructions would be needed.
Yeah.
And so if you had some, 10-digit binary number, in some ways that's more complex than a repeating series of 1, 0, 1, 0, an infinite series, right? Because I can write a program to write the infinite series is simpler than the program to write a single complex number.
So that gets into something we probably don't have a lot of time to talk about this today. Maybe we can defer this part of this discussion to a later program. But Ivan, that really tickles something that I've thought about in the past, and that is that a pure random collection of information, whether it's random orientation of molecules in a gas, whether it's random bits on a disk, etc., or an optical medium, it seems to me that randomness has in some order of measure more complexity than order, because like you were talking about with the 1 0 1 0 1 0 1 0, you can specify a formula to reproduce that fairly easily, but a purely random system has very little structure, and the only way you can reproduce it is to specify it in detail. So it seems to me like a random system has more information potentially than an ordered system. Does that sound reasonable?
Yes. Well, that's why in information theory and the theory of communication, the more bits you shove through your communication channel and the more efficient you make it, the more the result resembles random noise.
Wow. So that's what some of these compression algorithms and whatnot.
That's right. If you take a compressed image and you look at the bits, unless you know the compression algorithm, they look pretty random. And in fact, I've used that approach as a way of making an approximation of true random numbers for simulation. As a digital astronomer, I have access to vast amounts of image data. And then what you do is you take it and you compress it. And then just to stir it up even more, you encrypt it. And the result of that is indistinguishable from the result of a random process, unless you happen to know all the secrets of how I generated it.
Wow. Yeah, that's really interesting.
Wow. Yeah.
Thank you.
There might be some distinction that you could make, though, between the like if you were trying to measure what is the complexity of like a physical law versus a particular system, right, that can exist under the physical law. So in other words, if I have an instruction in my algorithmic instruction set for generating a random bit, I can make a very simple program that generates random numbers.
Right, a random
yes,
bit.
But then that doesn't fit the definition of what you're talking about, Kolmogorov complexity, because the question is, how complicated a program do you need to generate a specific sequence?
Right.
Yes.
And that's an interesting question. One of the other problems with the concept is that given suppose you have a program that generates a particular sequence. In general, it is impossible to prove that that's the simplest possible program.
Wow.
And so all you can do is you can put an upper limit on the complexity of a sequence, but you can't actually determine the complexity of a sequence using this theory.
Could you apply this to part of what we've been talking about today with the complexity of molecules or the complexity of biochemistry? Is there some algorithmic way to approach this problem, do you think?
How would you do that?
I would think, I mean, I agreed in general with your original statement that measuring complexity is difficult and that we don't really have a really good way of doing it. And I think part of the reason is that, okay, so we've got this idea of algorithmic complexity. This is one measure of it. But then applying it, it's like, how exactly am I going to apply it? Like, how many parameters does it take to describe the kind of complexity that you want to describe?
Right. Wow.
And then can I, in practice, actually sensibly talk about algorithms that do that?
One way to do it is that again, this will give you an upper limit, but one way to do it is that there are standard ways of describing chemical compounds. And then you could take that standard, you could take a standard description of a chemical compound and then apply the best data compression technology you know to it. And you would wind up with a string of bits, and that is an estimate of an upper limit. That's an estimate of the Kolmogorov complexity. It's an upper limit, but that's about the best you can do.
Hey, Joanne, I've got a question for you. Is there a way to write out a chemical formula that reflects the geometry, the isomer?
Yes. Yeah. We have organizations. One of them is the International Union of Pure and Applied Chemists. And of course, we cooperate completely with our brothers and sisters in physics. The nomenclature is clear. However, the book itself, is about this big.
Yes.
And there are huge arguments that go on between one set of people and the other set of people as we come across new things, and how do we do it, and what's the order, and who's on first, and who's on. And
So it's not like your high school chemistry where you write, C12,
No.
H24, etc.
No.
It's
There is an actual nomenclature for this. It is clear. It is unambiguous.
And unreadable.
You just can't read it. Yeah.
All right. Well, it's time for us to wrap up today. I've really enjoyed the conversation, and thank you so much for the presentation, Joanne.
Wonderful to see you guys again.
Everybody, we thank the American Humanist Association, who in part has made this program available to us through a grant that has purchased some of this equipment and software that we're using, and
the man upstairs.
paid for the Zoom. We thank the man upstairs, my husband, Dave Clark, who joins us occasionally and is our technical guru. We thank our panelists, Abby, John, Ivan, and Mike, who had to leave us early. But we'll be back in a couple weeks. And before that, we'll post on the meetup for the Prairie State Humanists, the local humanist group. We'll post information about what our topic will be in 2 weeks. So thank you all for joining us. Keep safe.
Good
Enjoy
to see you guys
spring.
again.
And
Be well.
we'll see you again soon.
Thanks for doing the presentation, Joanne.
Oh, thank you.
Thank you.
Happy Halloween.
Is I Beltane only? Is that an amino acid?